You guys, does anybody hear me?
Yes.
Let's see how this works. Tell me if you hear me clearly or not. Dominic, are you connected, man? You have a mic? Is it good?
Yes, I do.
Yeah, you guys are welcome to share your video too. If there starts to be a problem, then, I turn it off. You don't have to show your video, but I'd like to see a few faces.
Sure.
It's better than talking to an empty screen. Bye.
Does this work?
Yeah, it's good. It's all good. Oh, Chen-Chi's there. Okay, he's connecting.
Hi.
Hi. So please remind me, Chen-Chi, if I forget to say something or forget to point out something about the class.
It's okay. Will you show how to register into Jupyter Hub?
In OLAT to
No,
sign up for
from your
Doodle?
slide.
In the Doodle or the OLAT?
No, from your slides. There's a link. You click it, you will sign up.
Oh yeah.
Jupyter Hub.
By the way, let me just share the link to the slides right here on the chat. I mean, I already shared all that stuff by email, but let me just do it again here. Just a moment.
Yeah, the Doodle. The slides.
And you can put the Doodle link for signing up later when we get to that. Okay. Yeah. The sharing link, not the edit link. Okay. Yeah. Okay. Anybody have a question right now? There was some confusion about the course starting time because nobody noticed, that the university had a different starting time than what ETH put us. Some reason the course was rescheduled in ETH in my studies for 2 to 4 instead of 1:15 to 3. And nobody noticed that happened, first of all, and then they didn't notice that university still listed the course at 1:15 to 3. So we have to go with since the leading house for the course is ETH, we have to go with that scheduling because I assume that's what most people would find in the catalog. So that's the situation right now. Yeah, it's a different world now, isn't it?
Indeed it is.
More relaxing, man. You can sit on, you don't have to move around so much. Everybody's going to get a bit fat. Not moving around their bodies as much. But in some ways, we're going to be much easier.
Yeah, I'm really curious to see how these lab courses are going to work now that we don't really have a physical presence.
Well, these guys have been working so hard on this new class chip, and it was only because of this new class chip that the whole thing was possible. And, first there was the long work on the class chip itself, which started with a master's student. Then that had to be turned into an actual chip design, that was verified in LVS and it had to be taped out. The chip had to be gotten back. A whole PCB had to be designed. Firmware had to be written. Software had to be written. And then the last thing, just last week, they were going to make everybody install a virtual machine on their own computer and then physically take the board and plug it into their computer. But there was a shortage of such boards. So now Chen-Chi worked like hell to set up a Jupyter Hub so that he can plug all the existing boards into his own PC and host the lab sessions there. So remotely, he'll tell you all about that later. But this is really a first time that we've used this new silicon. It's functional, thank God. But you guys are going to have a much, much, much easier time doing your laboratory exercises than in the past because you won't be physically, unfortunately, in some sense, you won't be physically plugging in the wires and the chip and handling all the equipment. So you won't learn how to use all these source measure units and oscilloscopes and stuff like that, unfortunately. But on the other hand, it'll let you focus on the device physics and do the measurements much more easily. Because before, a lot of the groups were just debugging for the entire laboratory exercise because they had the chip not plugged in properly or some wire was not in the right place. And it was really a nightmare for them to get to all the actual experiments that they were supposed to do on the transistors were obscured by this headache, this baggage of configuring the DUT, the device under test. So it's going to be a lot easier. So welcome everybody. Now I'm Toby Delbruck. I'm going to be giving the first 3 lectures in Neuromorphic Engineering 1. And first of all, I encourage you to ask questions and to use this participant list to make me go faster, go slower, raise your hands. If you have a question, feel free. There's no such thing as a dumb question to interrupt at any time. The recording of the lecture, which I'm going to play, and I'm going to take pauses also to ask you for questions, because no point in just listening to a recording. You might as well ask you questions that are bothering you. That's the whole point of having a live lecture, right? So you can ask those questions, which we haven't anticipated. And at the end, we're going to give you a poll to ask you whether the material is too fast, too slow, and ask a few questions like that. So I'm going to start the lecture off, and then Chenchi, I assume, will take over to talk about this new class chip design that we developed for teaching this neuromorphic engineering course. Are there any questions right now? Okay, so in that case, let me attempt to start this. You all have the link slides already. If you've know all the material already, except for the class chip, don't bother to waste your time. But if you don't know, it'll be interesting for you because it's the core fundamental physics of devices, of semiconductor devices. So I'm going to attempt to now do it on the screen here, and yeah, so let me stop that for a moment. Usual problem. Okay. I'm going to now share the screen of this tablet. It's clear? Okay, and I'm going to keep the chat window open. So if you have any questions, just ask them. Raise your hand. Like I say, make this interactive, please. Apologies for the hiccups. Oh, I forgot to do something. I have to do. Sorry, guys. I have to share my screen properly. Would think somebody that's using Zoom now for so many months would know actually how to do stuff, but it's clear that I'm still not doing it properly. Okay. Welcome everybody to Neuromorphic Engineering 1. Okay. I'm Toby Delbruck, and together with Giacomo Indiveri and Chi-Chi Liu, we're going to give the lectures on this class, which takes place on Mondays from 1:15 to about 3 o'clock, always at the same Zoom link. The lab exercise location will be online via Zoom sessions with your TAs, and I'm going to share the link to the slides here, or we'll share the link to the slides here on the Zoom chat. It's a 6-credit point. The oral exam is 20 to 30 minutes at after the end of the semester, and the laboratories will. Did it stop? Is it broken right now? Yeah, it's annoying. I'll just give this first slide by hand. Can you still see it? Can you hear me? Yes or no?
Yes.
Okay, thank you. Okay, so you can see your teaching assistants here, and this is annoying. Okay, so you have to successfully complete at least 9 of these lab exercises, and you have to do at least the first 3 lab exercises. That's mandatory, and at least one of the last 2 labs. If you do all the laboratory exercises, will drop your 3 lowest lab grades. And the grade ultimately of this course is going to be based on 70% oral exam and 30% your exercises. The lectures are going to be given by myself, Giacomo Indiveri, and Chi-Chi Liu. And the last lecture, I think, will be given by Malika Pavand. And your teaching assistants are Elisa, Georgia, Chenchi, Karsten, and that's it, I think.
Toby, I think we don't see the slides.
Oh, you don't see them anymore? Okay. It's annoying. It's definitely not working. Pickups here. Okay. Okay. So what we're going to do today is introduce the book and arrange lab times via Doodle and introduce the new class chip, which is the biggest change we've made in the last decade, and the exercises via Jupyter Hub. So you'll be able to do this from the comfort of your own keyboard, wherever you are, to a Jupyter Hub, which is talking to a real hardware chip. And then there's going to be a long introduction to device physics for complete beginners. And then at the end, the TAs are going to demo the lab setup and the class chip use in Jupyter Hub for you. So stick around for that. And the recordings of every lecture that we give is going to be on the class Switch Tube channel. Okay, so let's take a look at our composition this year. It's quite mixed. If you look at, there's 50 people registered. That's you guys out there. You know, they're mixed between biology, biomedical engineering, neural systems and computation master students, electrical engineering. There's some computer science and ETED students, some physics, special students. I'm not sure what those are exactly. I think they're coming in from university. It's quite a mixture of disciplines. Also, the kind of the program, there's some molecular biologists, some NSC students, electrical engineers, biomedical engineers. Again, a quite mixed, broad audience. Some people have a lot of electrical engineering before, others had almost 0. And the language is 30% German. I think, don't remember what this red thing is here. I can't see it right now. But yeah, broad mixture of languages. Class is all going to be taught in English. Okay. So the textbooks for this course are the introductory textbook. You can get the Amazon link from the slides. Is Analog VLSI Circuits and Principles. That's written by us about a decade ago or 15 years ago. And there's a more recent book called Event-Based Neuromorphic Systems, which is all about systems of neuromorphic chips and robots and so on that are based on the idea of transmitting spike events instead of Nyquist samples. So what is this course about? Really, it's about learning a Pidgin vocabulary. Pidgin means like the most basic vocabulary that everybody can speak when there's a polyglot of different cultures that come together. And a Pidgin vocabulary is like a very basic vocabulary of circuits. And here you see different classes of circuits. So here you see an N-type transistor, P-type transistor, capacitor. Almost everything we built is composed out of these 3 things here. But within this class, you have the NFET, the PFET, the capacitor. Then you have a basic amplifier. It's an inverting amplifier. You have an NFET transistor going into a current source, so fighting it out for the current, and that results in a high voltage gain. This voltage goes up. The current here tries to increase. It gets bigger than this current. The voltage goes down a lot. You have basic elements that are used in all differential amplifiers, a diff pair, where you compare 2 voltages and turn that into a difference of currents that share a common bias current. You have other things that are composed from a diff pair and a current mirror, which copies a current, to form a transconductance amplifier, where it takes a differential voltage and puts out a current that's proportional to the difference of the voltages when the voltages are small. and so on. Many, many more circuits that can be composed out of these high-pass filters, edge-sensitive inhibitors, band-pass filters, current correlators that take a pair of currents and basically multiply them together to get the output current, which is normalized by the sum of the currents. A bump circuit that takes a differential voltage and turns it into three currents. One that gets big if either one of the voltages on the input gets big, and one that's big if the voltages are similar. Yeah, it goes on and on. So by the end of this course, you should be able to look at all these circuits and reason your way through them. And you'll have a good understanding of most of what's on this page by the end of the semester. And you'll have measured many of these circuits with your own hands, at least through the computer interface to our class chip. So you should recognize, by the end of the semester, you should recognize many of the circuits and be able to reason your way through them. By reason, I mean that you'll understand, you'll have some intuition about how the voltages affect the currents in these transistors and how those interact with each other. And so you'll be able to say, okay, if this gate goes up, that means that this drain current will go up. That means this voltage will go down, and that will cause, something else to happen. So you'll be able to start reasoning that way about these circuits and understand a new circuit, even if you haven't seen it. And that's the first step to be able to synthesize your own circuits. Okay, so now I'm going to tell you a short history of neuromorphic electronics. What is it all about? And if you're interested in more detail of this very interesting history, see Shichi Liu talk from 2020 Neuromorphic Workshop. There's a link here to the YouTube video of that whole talk. It's quite entertaining if you have an evening free or something like that. But the context of all this work on neuromorphic electronics, neuromorphic electronic computation has to be set in the context of silicon electronics. So I'm sure many people have seen this 1947 picture of the Bardeen and Brattain point contact bipolar transistor. This is basically the first demonstration that you could amplify the flow of current by the application of a smaller current in a semiconductor device. Okay, this wasn't very practical, but this is 1947. By the year 2000, when I took this wafer picture here, this 8-inch wafer, it was absolutely routine now to fabricate wafers with billions of transistors on them. In fact, we're completely surrounded by this technology. It's the dominant computing technology of history. And so it's very interesting to consider how that's really happening, right? You have a physical world, which you have to sense and you have to control somehow. And in between is all the computing. Now, what is the type of computing that most devices do? You guys who are computer scientists know this stuff very well, have done digital chips. But for people who just run programs on computers, it's interesting to understand what's the nature of that digital computation. Is it different than brain computing? Well, it is different, but the main point about neuromorphic electronics is also quite analogous. And you have to understand that, first of all, that everything on these chips that people build is based on just two kinds of devices, really, two kinds of active amplifying devices. Two kinds of transistors, right? A P-type transistor, which conducts holes, positive charges through the channel, and an N-type transistor, or negative, which conducts electrons, negative electrons through the channel. And these fight it out. That's why it's called complementary metal oxide semiconductor, right? Because you have a metal, an insulating oxide, and then a semiconductor. So this complementary metal oxide semiconductor, or CMOS technology, always consists of complementary pairs of these PFETs and NFETs that fight it out for what the voltage is between the positive branch, which is the positive power supply, and the negative branch, which is the ground power supply. See here you have a metal wire, and this is a side view looking into that. We'll talk a lot about these transistor structures, but that's what's doing all the computing. Whether it's a digital chip, analog chip, that's basically the devices that are doing the work. So now I'm going to tell you about artificial real-world computation, or how industry thinks of analog computing. The way they generally think of analog computing is that at an input you have an analog to digital converter, here cut off a bit, that quantizes the analog signals of the physical world into quantized digital symbols. And at the output you have a digital to analog converter. That takes the digital symbolic binary representations and turns them into analog values, and in between you have just logic circuits. logic means just 1-0 circuits. And the way those circuits are architected, the general scheme for building such synchronous logic circuits, as outlined way back around World War II and written down by in the famous book, The Computer and the Brain. The name will come to me in a moment. But anyway, this is the architecture. So synchronous logic is ubiquitously used to implement finite state machines, or FSMs. And the way it works is that everything is called synchronous because there's a clock, right? There's a big clock driver, or actually a clock tree, that broadcasts this digital signal throughout the chip, goes up, down, in a regular way. And every time that clock edge comes along, a bunch of registers, which are memory elements, 1-bit binary memory elements that store the state of the system, copy from their input to their output. And in between the clock edges, the output of these registers doesn't change. And then the outputs of all these registers, which form some kind of state or a value of your computation, exist on a logic bus, which is many wires representing a digital signal. And it goes around that bus and it goes through combinational logic. These are ANDs, ORs, and inverters, which implement the state transition conditions of your finite state machine. And so it's called combinational because at any moment, the output only depends on the input at that moment. There's no memory within this combinational logic. All the memory is right here. And so now this combinational logic, together with the previous state, plus external input. So suppose you have an adder, right? So the external input is the new number you want to add, and then the computation is expressed in this combinational logic. Combines the new number plus the number that's already in your register and adds it up. This whole thing then goes along, and every clock edge, this filtering happens. And the key thing that makes this all work is because you can precisely simulate this stuff, you can guarantee that by the time the next clock edge comes along, the longest possible path through here will have settled down at the input to these registers. And so you guarantee when you latch this value in this register, copy it from input to output, that it's going to be good. It will have crossed the logic level. And that's how it's possible to build big digital systems with hardware description languages and silicon compilers, synthesis, that all kind of computer systems are built. And this is a really great way to build chips. I mean, it really works and it has many advantages. But the problem is that the elementary math operations, say, for example, even at 8-bit precision, require tens of thousands of transistor gates to swing rail to rail. That means that a bunch of transistors have to move all the way from 0 all the way up to the power supply, or vice versa. And it includes the memory elements that may be on the same chip, but actually quite far away. And so it takes tens of thousands of these transitions to do even rather low precision mathematical operations for each operation. And so although this provides a straightforward way to construct and reliably manufacture computation, the result seems very energy inefficient. And so let's try to contrast that with biology. So the motivation from biological computation for all this neural engineering comes from natural computation. And if I had the video here, you would see the bee flying around and foraging and recognizing these flower patterns and doing acrobatic flight and doing all kinds of stuff. And even nowadays with a 10 kilowatt computer, with the very best drones that we can build, we can't do this task reliably. I challenge any robotics lab to really do it, especially on the power budget of this bee, which is well under probably 100 microwatts for the whole brain. And so this bee can fly aerobatically, it can recognize patterns, it can navigate to the foraging site, back to the nest using a variety of cues like polarization of the sky and odor and time of flight, and it can find new food sources and go back to the nest and tell the bees where that is. And this is all happening on, I don't know, probably more like 100 microwatts of brain power with only 1 million neurons and 1 billion synapses. That's less synapses than you have in an Xbox processor. And we estimate that it's doing about 10 operations, 10 like synaptic operations per second per synapse. And so we can, from these numbers, we can estimate that the cost of this computation in the bee's brain is about 10 to the minus 15 joules per operation. An operation, like I say, is a synaptic operation. synaptic activation. So 1 femtojoule per operation. That's what the bee's brain is burning. Now compare that with a logic transistor. We know that digital silicon is anywhere from 10 to the minus 7 to 10 to the minus 13 joules per operation. So biology is anywhere from 10 to the 8 to 1,000 times as efficient as digital silicon. So that drives the original motivation for neuromorphic engineering, was to try to close this huge efficiency gap, because you knew that if you had to do everything digitally, then it would just burn hundreds of watts or kilowatts to get to any level of reasonable computation. Okay, I should ask if there are any questions. I'll pause. So let's then look at the computer versus. Any questions? Any debate? How many people, I just asked right now, raise your hand yes if you've done, let me show the participant list here. Raise your hand yes if you've done any digital IC design. And I'll just look at a poll. Okay, so two people. Oh yeah, you raised your hand. Yes, yeah. So some of you people who probably have electrical engineering background have done logic circuit design. Many people have not. Okay, you know that logic circuit design is quite automated now. I mean, it's a skillful operation, but in some ways it's like writing programs. Yeah, we can debate a lot about this. Anyway, it's not central to the course, because the course is really about learning transistor analog design, which is difficult, a difficult thing to do. Okay, so I'll just continue then. The computer and the brain. See if I can do it. Okay. So let's then look at the computer versus the brain. Over here you have a AMD Ryzen chip. It's 192 square millimeter, really big piece of silicon, costs about $1,000 or several $100 actually to build this chip. Has about 5 billion transistor. It burns peak 180 watts. So it's really like a very powerful light bulb in this little tiny, 2 centimeter square piece of silicon. So that's why they have to put these big heat sinks on these gamer PCs. So there's lots of stuff here. You see like the different computing cores. There's 8 of them. The level 3 cache. Within each core, there's level 2 and even level 1 cache. There's lots of interconnect. There's the DDR4 channels to connect to DRAM off chip. Complex architecture, all designed by that digital design technology approach that I just talked about. Compare that with a piece of Cortex. So here you have a cross section of a piece of Cortex. You have one pyramidal neuron. That's the kind you have up here. The whole thing's about 0.5 millimeter thick, and it consists of different layers, but we're just looking at one neuron. Now, the green part are the input dendrites of the neuron. You see it here, it actually has 2 dendritic tufts, and the red part are where it sends its axon out to other neurons. Okay, so this is just one neuron in a whole vast 3-dimensional kind of mesh of neurons in your brain. The red is axon, like I say, the green is dendrite. And in a cubic millimeter of cortex, you have about 100,000 neurons only, but you have 1 billion synapses. That's in each cubic millimeter, 1 billion synapses. And that cubic millimeter of cortex burns about 1 milliwatt. Quite different technology. Main thing is that the mobility of the devices is so vastly different. Here you have electrons moving through silicon, almost like in a vacuum. And the mobility of these electrons in these silicon wires and metal wires is about 10 million times higher than the ions you have in the solution-based electronic computation of biology. So it's a factor of 10 million in the device mobility, which is something I'll talk about later. So the observation is at the system level, brains are about 1 million times more power efficient than computers. The question is why? So we already saw that the cost of elementary operation, the turning on of transistor or activating the synapse, is about the same. I didn't tell you. Remember I said it costs about a femtojoule to turn on a synapse here? Actually, it costs about a femtojoule to turn on a transistor here. Actually, a fraction of a femtojoule, about a 50th of a femtojoule in the most recent technology. So it's not some magic about physics, why this is so efficient over here and this is so inefficient. It's really about the organizing principles that are used. And then you have to compare computer versus brain principles, like the fact that a computer has a fast global clock. The brain is self-timed, uses sparse computation. The average spike rate in your brain is only about 1 hertz compared to these gigahertz frequencies we have in these kind of chips. A computer uses bit-perfect deterministic logical state. That means if I could freeze the digital machine at any clock cycle, I could predict exactly the voltage of every node. But in the brain, you certainly can't do that, right? The synapses are stochastic, and they only have 20% probability of activation, and the computation continually dances between digital when the neuron is spiking and analog inside the neurons, and then back to digital again when it spikes, back and forth, right? And in the computer, the memory is distant in time and space to the computing, right? This level 3 cache is many, many clock cycles away from the core computation. And the DRAM is hundreds or thousands of clock cycles away. So if a processor here wants to access DRAM, it has to stall for several hundred or even thousand clock cycles before the memory comes in from the DRAM to process. So it's distant, it's far away. But of course, in the brain, all the memory is in these synaptic connections directly between the neurons. And then there are other things like the devices are frozen in fabrication for this computer. And the brain has this beautiful molecular computation and biochemistry that continually adapt itself and modify itself throughout life. Okay, so these are very general observations that don't really help you understand, how to build stuff specifically, right? Still interesting to consider. But it was these kind of observations that led Carver Mead here, who was a physicist by inclination, invented the gallium arsenide MESFET transistor, and he's the person who actually coined the term Moore's law for Gordon Moore. This continual increase in transistor density. And he was also the co-author of this Introduction to VLSI Systems. It's a main logic design textbook for 20 years. You can check out in 2013 this ISSCC, International Solid State Circuits Conference, keynote talk, where he talked about his work on throughout the years. It's a cool talk. He's a wonderful speaker, very clear. And he's well known as the high priest of silicon. So he got interested in this idea, right? After he established digital circuit design, he could see that it was going to become an industrial effort. He established an effort towards neuromorphic engineering. He just thought that was an interesting intellectual problem. And so you can hear much more about that in Shichi's talk. But he wrote in this paper in Proceedings IEEE Neuromorphic Electronic Systems, he said, the fact that we can build devices that implement the same basic operations as those the nervous system uses leads to the inevitable conclusion that we should be able to build entire systems based on the organizing principles used by the nervous system. So that's like the mission of neuromorphic engineering. So take a look at this talk from Carver, take a look at the talk from Shichi eventually. It's good to have the cultural background and know who did stuff. And I hope you enjoy that cultural stuff. And now I think we're going to take a look at the exercises. Okay. I'm not sure what happened. I somehow stopped sharing the window. I'm going to now share, I don't know, Chenchi, if you want to share the slides there or how you want to do it.
Can you continue sharing slides?
Okay, so I'll just go back to the slides. I think this part is not actually recorded. Let me attempt to do that again. I'm having a bit of difficulty here with my Zoom skills. And by the way, first of all, let me just ask, are there any questions right now? Please show yourself, raise your hand, whatever you have. I see a bunch of hands up. Maybe they're still up from before. Basically, by the way, in Zoom, you have to lower the hand explicitly. So I'm going to lower all your hands for you and then raise them again if you have a question. Okay, so, oh, I see. Hajar, you had a question, but now I see it's gone again. Okay, you're happy? I'm happy then. So then let's just go on. All right, so I'm going to try to show this again. Let me try to do this properly here. Yeah, I'm going to share the actual screen. So I guess I'll just advance for you. Where the hell is the mouse, man? Okay, so now I'm going to pass. Okay, like I said before, on this class chip, this brand new class chip, you have many, many, if not all of these circuits here, which are just sketched out as transistor circuits here, which is the way you'll do them on paper, hopefully. And now Tenchi will tell you about the exercise. Stupid thing is going forward.
Okay. So basically this year we'll be holding exercises through your browser, and you will access a chip. Oops, I have to unplug it. Do you see it?
Yeah.
Yeah, you will access a chip like this, which is hosted on my PC, and the labs are done despite it's remote in groups of two. By one of you will join with Zoom, and the other one will join with the Jupyter Hub. TLJ is just the abbreviation for the Littlest Jupyter Hub, which will host the exercise sessions. And the first 3 labs, I don't know, this is not updated. The first 3 labs will last 2 hours, and the rest will be 4 hours. The materials, I will show later how you can access it. But you will also have to sign up on the Doodle link, which we will. Wait, Toby, I think this slide is not.
It's slightly out of date. Yeah. So just they have shared with them the up-to-date slides, but this is the one that I recorded.
Yeah. Okay. Okay. Fine.
So just tell them right now what is the actual condition that's different than this one.
Oh, the condition is you don't have an individual pre-lab because we consider it's not really easy to do with remotely, and you do everything in group.
So and you each hand in the same group report.
Yes.
Yeah.
But each one has to hand in through your OLED Dropbox. But 2 of you can have the exact same lab report. I mean, you should have the exact same lab report.
But it has to be signed by both of you. They're both taking responsibility for that lab.
Yeah.
And, basically it's up to you to learn, right? But, if you're the second wheel and never actually do anything, then you simply won't learn the material. Okay.
Yeah.
Okay. You have any questions about this labs? Contact Chenchi directly.
Yeah.
He's the point of contact for the lab exercises. Okay. Don't contact us, professors. We're kind of a changing crew. The central point of contact for your exercise is going to be Chenchi, at least for the first labs.
Mm-hmm. Yeah.
Okay. Okay. Now, what do you want to say about this? Stupid thing is going forward.
You can. This is I mean, in the updated slide, you will show the sketch.
Okay. So in that case, I'll just switch over to the actual one, which is up to date for this section. Let me just open that. Apologies for the hiccup here. Where's my folder? Okay, that's hidden here. Now I have to go forward. What number was that? Like 17?
Yeah, 18, 19. Oh.
Okay, well, this slide is the same.
No, I changed the content a little bit. So you will have you will click by the link of lab 1 when you come to the lab session, but don't click too early because I have to create an account for each of you after you have formed your groups and you come to the lab session. I will create an account and you click the link. Toby, can you click it?
Now it goes over to a web page, which I'll show you here.
Yeah.
That's the web page.
Yeah, and I have already created an account for Toby, so you can enter your name as Toby and set a password in the first time when you sign in which case you can set a password now, Toby.
You can just set it as something, I don't know. Okay.
Anything, yeah. And when you sign in.
Oh, cool.
Yeah, and I think you need to sign in back again.
Okay.
Oh wait, you didn't click the link. I think it is not the link.
This link?
Yeah.
I did click it. You want me to just copy the link directly and open it in the browser?
Yeah.
I can't easily do that. I'm not sure why. Now I definitely click the link. The notebook is empty. Okay, so this is the procedure you should do. It should work for you
Yeah.
that you assign into the lab that
And
way.
then you will also get the materials downloaded to your directory.
Right, you should get them downloaded. If there's some problem, then we'll sort it out. But you know, the very first lab exercise is just about automated data acquisition and analysis, and basically not even running the chip, but just the very first steps. If you've never used a Python notebook before, never plotted anything, never did anything with Python. And now I need to ask a question to everybody. What's your background in Python? So have you had some significant background in Python? To everybody, say yes if so, or no if you haven't had any Python. Okay, now I'm looking at the participant list. I don't know if you can see it if I put it over here. I see yes, many people have had Python, but some people have had no Python, and other people are just not answering. Yeah, so a lot of people have had Python, other people have not had any Python experience. Now, my recommendation for that is if you can find a partner who had Python experience, partner up with somebody who doesn't have the experience. That's a really good partnership, because then the non-Python person can learn something and you know, quickly solve the dumb mistakes. And then they can gradually take over responsibility in later labs. Okay, is that helpful? Can you see the participant list when I share it like this? I'm showing the participant list on top of the screen. Can you see it or not? No, oh, you can't see it. Okay, but anyway, you can look at the participant list yourself. Okay. Oh, I see. You guys are typing no. You're supposed to use the voting link at the bottom of the participant window. At the bottom of the participant window, you guys who are typing no into the chat window, actually go into the participant window, and at the very bottom, you should see this yes, no, go slower, go faster buttons. Do you see those? Say yes if you see them. Or just tell me yes, you know, turn on your microphone and say yes. Okay, everybody turn off your yeses now so we can reset those. Okay, good, so let's go on then. Okay, so that should work. Now, you want to talk about the class chip a little bit? I can say a few words about it, but you know much more about it.
Go on.
Okay, so for many years, we used a fully custom chip that was built in, I believe it was 2 micron technology. So you could tell how old it is because the feature size was 2 microns. It was a wonderful chip because you could get direct pin access to all the devices. So about 2 years ago, or maybe a year and a half ago, we decided to go ahead and design a new updated class chip. And this is a 2020 class chip that's built in 180 nanometer Austria Microsystems technology, which is a great analog technology from Austria Microsystems, who has a strong presence also in Switzerland. So here is actually a layout picture of this class chip. It has a big bias generator. It has all kinds of test circuits. It has output buffers to drive the outputs. Has lots of stuff, and you can see the architecture over here. It has a core with Synapse Neuron Bank, multiplexers and demultiplexers to let a few pins from the outside address all these different circuits inside the chip. It also includes a digitally programmable bias generator that we use on a lot of different neuromorphic chips and sensors. And it's controlled digitally by address event representation logic interface. And what's a C2F bank? You know what that is?
Frequency.
What is
so
it?
Just for measuring small currents. It changes.
Oh, current to frequency. Yeah, current to frequency. So the current, a device in here may produce a very small current down to say picoamps. It drives into here and that turns it into pulses, which then can be measured off chip by the microcontroller, digital, counter timer. Okay. And so the partial contents of this class chip, here is actually a list of the test chip circuits, NFETs, PFETs, arrays of transistors, so you can measure matching or effects like the effect of transistor length on the drain resistance. It also includes circuits like a source follower that are a very useful buffer circuit that allows you to also measure things like the backgate coefficient, the kappa, diff pairs, transconductance amplifiers, wide output range transconductance amplifiers where the tail currents are mirrored And so it isolates this differential stage from the output stage. Current correlators, bump circuits, current splitters, and also time domain circuits like follower integrators. This is an RC low pass filter, which you can measure filtering properties. Lots of other stuff, lots of neuromorphic stuff on here too. All this stuff is accessible through a programmable digital interface to the chip. And, you know, so now you don't have to fight your way through plugging in these little jumper wires to the board and getting things flipped around, ideally, although it's still a work in progress. And the whole thing is hosted on this lovely PCB. Chip plugs in here. It's called Coach, this class chip. And then it's controlled by a teensy 32-bit Arduino microcontroller that has its own 10-bit analog to digital converter. To measure currents from the chip, at least large currents, there's a current monitor transimpedance analog to digital converters that take a little sense resistor here and turn the current flowing into there is turned into a voltage, which they can read on the computer. Lots of other features on this lovely PCB, which is functional, although still being debugged. Is that a proper way to put it?
Yeah, the chip is functioning and the board is being debugged. Let's
Yeah.
put it this way. Yeah,
Let's put it this way. I mean, things are working, but not working perfectly yet.
Yeah.
So you guys are fortunate and unfortunate. Fortunate to be able to use this chip, unfortunate to be the alpha or beta users.
Yeah.
So you're setting the trend for the future. Okay.
Yeah, and I see some questions from the chat. I will answer them here because there's some students are asking what we're going to do in the labs. So I would say basically you will be using an analog chip, not designing a chip.
No.
So forget about
measuring circuit
so you set
properties.
some voltages, you set some currents, you measure some voltages, you measure some currents. Probably in the future you will set some parameters for a neuron and you measure the activity of a neuron, a silicon neuron or silicon synapse. Yeah.
You'll measure bandwidths of amplifiers, you measure nonlinearities, you'll measure whether things are stable or unstable. And you won't do, there's a question, will this course involve mostly FPGA coding then? No, definitely not FPGA coding. It's nothing to do with that. This is 99% an analog circuits analysis and measurement course. You can decide yourselves what your groups are. Basically, it's best if you find a partner. In fact, it's essential because there's so many people in this course that you must find a partner, at least for the first labs. Later on, it's possible that you could go solo, do the exercise, but right now we just don't have the time slots and the hardware devices that you can do it in less than groups of 2. And 2 is the maximum because we want to avoid the third wheel syndrome. Do you know in English they say there's a third wheel? 2 wheels always carry all the weight and the third one just kind of coasts along. Yeah, that we've discovered doesn't work. Yeah, and you'll be writing Python code to do the measurements and analyze the data and plot things and stuff like that. But ultimately, you're really doing hardware measurements, device characterization, as you would do in a real silicon semiconductor company. Any other questions? Okay. Yeah, so this is really cool opportunity. I think you guys are pretty lucky. Hopefully, if everything goes well, we'll get it all debugged. Okay. Now, how do you actually measure currents and voltages and set voltages? We don't have enough detail, but I'll just tell you the basic scheme. You can set voltages on this board using an 8-bit 2226 D to A converter. So it allows you to put in voltages, which are fractions 1/255 of 3.3 volts. So your voltage resolution on your D to A converter, I believe, is 3.3 volts divided by 255. Is that correct? It's an 8-bit DAC. Then you only have a voltage resolution of 3.3, 256 divide. So you can set your voltages in with steps of about 13 millivolts. Right, those are rather coarse steps, but that's what you get with this thing. That's unless you reduce the reference voltage on this digital to analog converter. You can also measure voltages using the teensy 10-bit A to D converter. The reference voltage for this A to D converter is 3.3 volts. And it's a 10-bit converter. It means it has 1,000 levels. So each count of your A to D converter will have 3.3 volts divided by 1,000, about 3.3 millivolt resolution. So one count on the A to D will be 3.3 millivolts. And then you'll be able to digitally select the circuits you have on the chip using a combination of on-chip multiplexers and off-chip multiplexers. You won't have to worry about that. You'll just call a Python API that will select a particular pin for you and connect it somewhere. And you're going to be able to measure large currents with this current power meter device in a 219. I never heard of it before myself, but it's a bidirectional current meter that basically it converts the voltage that is created across a resistor of 1 kilo ohm into a digital value. I don't know the resolution of that. Do you know, Chenchi? If Alex was here, I don't know, is Alex here? He knows for sure all this stuff.
Yeah, this is 12-bit and minus 40 to plus 40 microamp. I mean, range from minus 40 to plus 40 microamp with 12.
Yeah, so ideally the current resolution is 40 E minus 6 enter divided by 12-bit divided by 4096 levels.
Yeah.
So it's about 10 nanoamp supposed resolution, right? Yeah. A to D converter never really reaches 12 bits, so it's probably more like, 30 nanoamp resolution. It's a pretty large current on the scale of such subthreshold devices. So that's for measuring large currents. For measuring small currents, you'll use this current to frequency converter that I told you about before. And this will all be explained to you during the exercise. It's definitely an ongoing story. Okay, any questions about that? When are the lab sessions? We'll come to that when we look at the doodle. In fact, shall we look at when shall we reveal the doodle? Right now, so people can look at it, or at the end?
Seems some of them really care about it, but I would.
It's important to schedule the laboratory sessions, right? Yeah. We want to make it so that everybody has a fair shot at doing it.
Yeah.
Some people must have this course as a requirement, and those people definitely will give priority over the people that have as an option. We'll sort that out though.
Mm-hmm.
Okay. Okay. Okay, so then I'm going to go on. I think we should actually share the doodle now so that people who have heard this semiconductor stuff don't have to listen to it and can.
Yeah, and
we're going to take a short break. I'm going to take a short break now and let everybody sign up for a laboratory session slot. So could you put the sharing link on the chat here? In the meantime, I'll switch back to the recorded presentation.
I'll do that. Wait.
Okay. Maybe put the link and then I will look at that link. I will put it up here. And now you should go to that doodle. It's actually not just the first week, it's the first 3 weeks of exercises. We're going to be 2-hour lab source session slots, and they take place Thursday morning and late morning, and Thursday afternoon and late afternoon, and Friday morning, late morning, and Monday morning and late morning.
Yeah, and hopefully from the 4th week on, you will have the first lab on, you will have the whole morning or the whole afternoon having the lab session.
And the capacity for each exercise slot is 10 people exactly, because we have 5 boards, I understand. Is that true?
We have 3 boards for now. I mean, for the first 3.
Oh, so the capacity is going to be 6 people.
Yeah.
Means 3 groups of 2 people per slot.
But we will have many more boards later on.
Yeah. So we have kind of a slight crisis because most people are registered right now. But so sign up for this doodle link, and then I'm going to start playing the lecture, and then I'm going to give you a few puzzles along the way here, just to keep you awake. Okay? Any questions right now? That's great. There's somebody here saying, Leon Leonie Grossman says doesn't have much experience, needs a partner. Okay, so I don't know how you guys communicate. Normally OLAT, how many, first of all, say yes if you have experience with OLAT before. OLAT is the University of Zurich system. Okay, so if you, and no if you do not have experience with OLAT. Okay, so I'm looking at the responses right now. Some people are not responding, but I'd say about half of the people have some experience with OLAT, other people don't. Now, OLAT is supposed to be a forum, a forum, communication between people in the course. If something's not working in OLAT and you want it to work better, let us know. OLAT is a very complex, arcane, cryptic learning management system, in my opinion. I really don't like it so much, but it's what we have. And we can make it work better for you to increase communication, because you won't be physically meeting so much. But we want you to get to know each other because you can learn from each other. All right. Okay, so let me. Okay, so now we're going to start quite a long section of this lecture, which I'm going to take breaks, I hope, during. It's a first look at semiconductors and transistors. This will be heavy going if you don't have a background in this stuff already. So you're going to have to look at it several times and let it sink in. The concepts ultimately are quite simple, but somehow it's heavy going the first time you see it. So we're going to talk about metal oxide semiconductor transistors and semiconductor device physics. Remember, again, it's all about this structure here where you have, this is a side view of the silicon. You have transistors, either P-type or N-type, which are conducting current along the surface of the silicon, which is controlled by the voltage on these gates relative to the voltages on the sources and drains. And it's all sitting in a P minus substrate. The P FETs are built in N wells and the N FETs are built in P wells. I'll explain what that means later. So to understand all this stuff, we need to understand enough about semiconductors and junctions to understand how MOS transistors work. So we need to understand about insulators, conductors, and semiconductors. We need to know something about the crystal structure of silicon. And we need to know what's called the band structure. And what is the valence band, the conduction band, and the forbidden bands. We need to know about holes and electrons. And we need to particularly know about mechanisms of charge transport by diffusion and drift. We also need to learn about doping with the donors and acceptors, and a little bit about the Fermi-Dirac distribution and the law of mass action, where N concentration times P concentration equals the square of the intrinsic concentration. And we're going to finish with the PN junction and the reverse bias junction and its capacitance. And that will be enough to really establish a good firm foundation for understanding sub-threshold or weak inversion MOS transistor operations next time, when you're going to have to measure these things on the chip. So let's start by talking about donors and acceptors in the periodic table. So here you have a part of the periodic table where the middle is cut out. It starts with the noble gases over here. These are tightly bound. All the electrons in the outermost shells are tightly bound. And the atoms over here in column 1 are atoms with one extra electron in the outermost shell, like hydrogen or lithium. Then if you go from the left side here, you keep adding one more electron each time you go. And when you get to column 4 here, you get to silicon. And silicon has 4 extra electrons in its outermost shell. It's not a complete shell quantum mechanically, but it has these 4 extra electrons. Now the atoms just to the left of silicon are missing one of those 4 electrons, and the atoms just to the right, the elements just to the right have an extra electron compared to silicon in their outermost shell. If they're missing an electron, they're called an acceptor, and boron is an example of an acceptor because it wants to get an extra electron to make 4. And phosphorus and arsenic are widely used as donors because they have this extra electron. This will all become important later when you just talk about silicon and putting a little bit of dopants consisting of acceptors or donors into it to make it either P-type or N-type semiconductor, as I'll explain. So let's talk about conductors, semiconductors, and insulators. So an insulator is where the valence band, where the electrons are bound, and the conduction band, where the electrons are free to move, are overlapping.
So a metal is such a structure where the electrons, there's lots of free electrons to move around all the time. On the opposite extreme, there's such a thing as an insulator like silicon dioxide or quartz crystal. Same stuff as you see out in the desert. It's just silicon dioxide. Here you have silicon atoms, and in between they're bound together very strongly with oxygen atoms. And that results in a structure where the electrons are very tightly bound, and so there's a huge energy gap to go from the valence band up to the conduction band, 8 electron volts. Why is that a big gap? Because the room temperature activation is the thermal voltage, which is 1/40th, 1/40 of an electron volt. So 8 electron volts is 200 times the thermal activation. That's why there's so few carriers. And then you have stuff like a semiconductor like silicon, the one we're talking about here, where the silicon atoms are covalently, they share electrons with their neighbors, neighboring silicon atoms, and as a result the binding energy is not so high, and it only takes about 1.1 electron volts to go from the valence band to the conduction band. That's only 40 times instead of 200 times the thermal activation energy. And so why is all that important? Well, if we go back and look at this table of donors and acceptors in the periodic table, let's talk about what happens when you take silicon lattice and dump in one extra electron contained bound to a phosphorus atom, for example. So here is a silicon lattice with an electron donor atom, phosphorus. So there's the silicon lattice where you have all the silicon atoms that are covalently bound to their neighbors. And in the middle here, these covalent bonds. And then right here, what's that? Oh, that's a phosphorus atom, not silicon, phosphorus. Remember, phosphorus is column 5 element, has 1 extra electron. And actually these dots here indicate the approximate scale of the wave function of this extra bound electron. In fact, there it is right there. Of course, you can't really localize it like that quantum mechanically. It's just an indication of the scale at which you would see it. It's far away from the phosphorus atom. That indicates that it's weakly bound. So that extra electron is really easy to knock loose and turn into a free electron. Basically, it just conducts electricity. Okay? So the wave function of this bound extra electron is really broad here, and that just means that it is easy to knock it loose. Now, to understand why this is important, you have to understand that MOS transistors, metal oxide semiconductor transistors, use insulated gates to control barrier energies at PN surface junctions at the source and drain. Okay, so this conducting region here, which is a PN junction, so it's insulated, in some ways reverse biased, is connected to this side by this channel. But there's an energy barrier at this channel at this PN junction. Here's another PN junction. Okay, so the way you control the current through the transistors is by controlling the height of this energy barrier. I'm going to illustrate how that works here by this animated GIF. So here you have an N-type MOS transistor. It has a source voltage, it has a drain voltage, and it has a gate voltage. And right now, the source and drain are at the same voltage. So they're at the same potential energy. This is the electron energy going up here. The channel, which is a P region, it's unfriendly for electrons. It has a built-in energy barrier, is at some barrier height, which is set by the gate voltage. Let's assume the gate voltage is 0 here. Okay, so all the voltages are 0. Now, on the source and drain side, you have electrons that are flying around. Remember, they're not just sitting there. Even at room temperature, they're flying around at 100 kilometers per second. But they can't get across the barrier because the barrier is quite high. And so the number of electrons that actually have enough energy to get into this channel and cross over is very low. Okay? But what happens if you now put a positive voltage on the gate? Well, then the situation is, it looks like it'll attract negative electrons in, or another way to look at it is that it lowers the energy barrier. So now you put some positive voltage on the gate, and what the effect of that is it lowers the energy barrier. Because it lowers the energy barrier, more electrons have enough energy to get into the channel. There's still no net current because the number that get in from the drain side and the source side is the same. There's electrons whizzing back and forth for sure, but there's no net current. But what happens if you now take the drain and put it at a high voltage, high positive voltage? A high positive voltage is a low energy for electrons. Okay, so if you now take the drain and pull it up to high voltage, the situation looks like this. You see the difference? I go back one slide. I can't actually go back here. But anyway, now you see the situation from the source side. There's some electrons getting in, but from the drain side, that energy barrier is very high. So no electrons get in from the drain side. That means that there's a concentration gradient. Lots of electrons here, few electrons here. That concentration gradient will result in a diffusion, a net current of electrons from the high concentration to the low concentration. Just like a high concentration of gas diffuses towards a low equal concentration. And so that results in net current. And most of the circuits that you operate in this class, or for the circuits that we designed for these neuromorphic chips, operate in this region where the current is just going through the transistor by a diffusion process from high concentration to low concentration. So I'm showing you this now to motivate why it's interesting to understand p-n junctions a bit more, and the process of diffusion and so-called drift. Okay, so we need to talk a little bit about electrons and also holes. So far, I only talked to you about electrons, which are physical entities. And on this band diagram here, the energy of electrons goes up, right? Here you have the valence band.
Oh, I stopped it here. All right, guys.
And where the electrons are bound. When you give them enough energy to pull them loose from the silicon atom, they become free electrons, and then the more energy you give them above this, at the edge of this valence band, the conduction band, above the edge of the conduction band, the more kinetic energy they have, the more faster they're moving. At the same time, you also have holes, because every time you take an electron away from an atom, or if you put in a donor atom, you can have a vacancy in the lattice. That's called a hole. And quantum mechanically, as long as you're within the lattice, it acts just like a particle. It just has a higher effective mass, about double the effective mass. But now the kinetic energy of the hole, because the hole is a positive charge, it actually goes down, right? As you go down in this picture, the hole has more kinetic energy. It's moving faster. Okay? So that's why energy of hole increases down, energy of electron increases up. Why am I showing you this diagram? It's because when electrons are broken loose from the lattice and enter the conduction band, they become mobile and move almost as if in vacuum. On the other hand, holes are bubbles in the conduction band. The electrons move, but it's easier to talk about the vacancy, the hole moving, just like it's easier to talk about a bubble moving than about the water around it moving. And so holes have positive charge, and the effective mass, that means their acceleration under an electric field, their effective mass is 2.5 times larger for a hole than for an electron, having to do with the details of the silicon crystal structure. Okay, I'm gonna skip this here. Oh, yeah, so now I showed you this band diagram before. The reason I want to show you this is that this band gap between the valence band and the conduction band is about 1.2 electron volts, 1.1, 1.2 electron volts, which is about 50 times kT. Well, what's this kT business? Well, it has to do with statistical mechanics and thermal physics. So let's talk about a very important concept, which is absolutely central to the operation of transistors in weak inversion and subthreshold, and that's the thermal energy. So it's a basic fact that each degree of freedom in a system in thermal equilibrium is an average energy of kT over 2, where K equals 1.38 times 10 to the minus 23 joules per Kelvin is Boltzmann constant, and T is the absolute temperature. So for example, at 300 degrees centigrade, KT, this number here, is an energy of 4.1 times 10 to the minus 21 joules. Okay, so it says that each degree of freedom at room temperature has that many joules of energy, just thermal, on the average. Okay, so that's not very useful. What we care about in electronics is volts. So the question is, how do you relate this thermal energy to voltage? Any ideas about that? Okay. The way you do it is by defining a thermal voltage, which is kT, this energy, divided by Q, which is the charge of an electron. It's the voltage a single charge, elementary charge, falls through to pick up the thermal energy kT. Think about it. If you take this voltage and let the charge fall through it, you multiply the voltage times the charge, right? So this is the voltage. If you multiply this voltage by the charge, which is Q, you get back kT. So if kT divided by Q is a voltage, right? What's the level of that voltage? It turns out that voltage, well, Q is the elementary charge, is 1.6 times 10 to the minus 19 coulomb. If you just take 4 times 0.1 times 10 to the minus 21 and divide it by this number, what do you get? Well, you get the thing called UT, which is defined to be kT over Q, which turns out to be 25 millivolts, the magic 25 millivolts. It's 1/40th of a volt at room temperature. That's the thermal voltage, and that's the interpretation of the thermal voltage. The voltage the charge falls through to pick up the average thermal energy of a degree of freedom. And so it turns out that kT over Q, or the thermal voltage, is a natural scale voltage for electronic systems, or any system that uses charge in thermal equilibrium, whether it's silicon or biology, voltage activated channels. This kT over Q is always the voltage scale that matters. And you'll see that over and over again. All right. Okay, so now I come to something a bit difficult, which is the Fermi-Dirac distribution. It turns out that electronic systems are based on electrons, and electrons are fermions, and fermions are elementary particles that don't want to be in the same state. They resist getting in the same state. Unlike photons, bosons, electrons don't want to be in the same state. And so their statistics is defined by what's called the Fermi-Dirac distribution. It's Enrico Fermi and Dirac, who originally, I think, maybe not originally, I don't know the history of it, they derived this particular distribution that describes such statistical physics. And the way it's described is by plotting the probability of occupation of a state, a quantum mechanical state, versus the energy level relative to the Fermi level in kT units. Okay, so you see this probability goes from 0 to 1, as the voltage in kT over Q goes from above the Fermi level to below the Fermi level. So if you're below the Fermi level, that means the probability of the state being occupied is almost 1, and if you're way above it, then the occupation probability is almost 0. So the states, by definition, the states at the Fermi level are half occupied, and the states above the Fermi level are occupied with a Boltzmann distribution. If you just take this Fermi-Dirac distribution and take the limit of it, the probability of being occupied is exponentially dependent on the energy difference of that state relative to the Fermi level divided by kT. And then states below the Fermi level at lower energy are unoccupied with the Boltzmann distribution. The same distribution means the probability of not being occupied goes down exponentially as the energy gets lower and lower. So why does this matter? Because it's exactly this Fermi distribution that applies to the band diagram that we looked at before, the valence and conduction band diagram. And you can understand the concentration of holes and electrons by understanding how this Fermi-Dirac distribution interacts with these bands, these energy bands. Okay, so let's look at that. Let's imagine that we have these energy bands, the valence band and the conduction band and a forbidden band where the wave function of the states dies off exponentially. Right? So, but in the valence and conduction band, the wave function doesn't die off, and especially in the conduction band, the wave function can go forever, indicating a free particle. And let's look at an intrinsic undoped semiconductor. You don't have any donors or acceptors. In this case, you can compute from the crystal structure of the semiconductor, like silicon, you can compute a so-called density of states. As the energy goes away from the band edge, you get more and more states per unit energy. That's because there's more ways to fit the wave function in as the energy gets higher and higher. And so both in conduction and valence bands, you have this density of states. If you now take that density of states and multiply it by the probability that the state is occupied, which is the Fermi-Dirac distribution, then you have the actual occupation densities. You see here these bumps. It says that right at the band edge, there's very few electrons, and then it goes to a peak, and then it dies away to zero. And you can explicitly compute the form of these. They're just these functions here, which are like square functions, times this exponential. Okay, in this case, you have the same number of holes in electron because the semiconductor is undoped. But what if you dope the semiconductor? Okay, so let's go back again to the donors and acceptors in the periodic table and consider a phosphorus atom. They stick in there. And now let's talk about the level of doping. How much of this phosphorus do you stick in? Is it 1 out of every 10 silicon atoms? Or it turns out that actually it's a very small number. So the concentration or density of silicon itself as a crystal is about 10 to the 23 atoms per cubic centimeter. But the doping can vary from about 10 to the 15 to 10 to the 19 per cubic centimeter in practice. What that means is that these doping levels still represent only a tiny fraction of the total atoms, from 1 out of every 100 million to at most, at very heavy doping levels, to 1 out of every 10,000 atoms. So that means the donors and acceptors are really a very small fraction of all the silicon. So let's look at it again. Again, we have our phosphorus atom in a silicon lattice. It has its thing, its extra electron. And we know that the relative permittivity, that means the dielectric constant of silicon, is about 12 times that of vacuum. It's quite stretchy compared to vacuum. And we know that the energy of binding of an atom to its outermost shell is about the same as a hydrogen atom. It's about a half electron volt. To get the energy of binding in this dielectric, we take this original binding energy divided by the dielectric constant to end up with about a 20th of an electron volt, which is about 2 kT, right? Remember kT is 25 millivolts, and this is 50 millivolts. So the binding energy of this phosphorus atom is only about 2 kT. Why is that interesting? It's still bound with twice the thermal energy, but that's such a modest binding energy that in effect, all the phosphor, for every phosphorus atom that you stick into the silicon, all the electrons are contributed as free electrons. None of them are effectively bound, even though the binding energy is still twice the thermal energy. Okay, so the binding energy. Okay, so that's what I said already. Okay, so the basic answer and the reason that it's still free is that there are many more ways to be free than bound. Practically all the electrons from these phosphorus atoms that you stick in there, these donor atoms, are going to be free because there's just many more ways for them to be free than to be bound. All right, now let's take an N-type semiconductor. That's what describes an N-type semiconductor. We put in some phosphorus atoms to dope it, or arsenic. And what that does is effectively contribute a bunch of electrons to the conduction band, which is shown by this density of states here in this band diagram. And what that does now is it produces lots of free electrons and very few free holes, because it moves the Fermi level up. And if you compute this products of the density of states times the Fermi level, you get these new concentrations. Okay, I want you to compare this diagram with the one that I just showed you a moment ago. Remember the one I showed before where these bumps were equal size? Now the N is much, much bigger than the P. And it turns out that there's something called the law of mass action. And you know, if I showed you the P-type semiconductor where you doped it with boron, you know, with missing an electron, then you would get lots of holes and few electrons. It turns out in general, there's this thing called the law of mass action, where in equilibrium, the concentration of electrons times the concentration of holes is a square of the intrinsic concentration. So if you increase the concentration of electrons, you're going to decrease the concentration of holes. It kind of makes sense, right? You put more electrons in there, it's going to fill up the holes. And that product is equal to Ni squared. So it means in equilibrium, more holes means less electrons and vice versa. And Ni is the intrinsic carrier density, And at room temperature, Ni is about 10 to the 10 per cubic centimeter, or about 1 out of every 10 to the 13 silicon atoms. Remember I said the concentration in silicon itself is like 10 to the 23 atoms per cubic centimeter. So since the intrinsic concentration is only 10 to the 10 per cubic centimeter, it means only a tiny, tiny fraction of silicon atoms at room temperature is actually free. So basically all the free electrons that you get in silicon is from the donors and acceptors that you plant it with. You should also be aware that Ni increases with temperature because, the more the silicon is jiggled around by being at high temperature, the more atoms are going to be knocked loose. Okay, so now we need to speak about something quite important, which is electron transport. How do electrons move around? So we're going to talk about drift and diffusion, mobility, and the so-called Einstein relation. So first point is that an electric field causes carriers to drift. You can look at an electron here, which is bouncing around between collisions. So 1, it goes like a free particle, to 2, it collides, then it goes to 3, it collides. Every time it goes in a random direction after the collision. But if you now put an electric field on this electron that's moving around, it causes a little bit of extra motion of the electron. You see, like between 1 and 2, it follows this arc. Between 2 and 3, it follows this arc, and so on. So in between each of these collisions, there's a little bit of component of the electron motion in the direction of the electric field, or actually opposite to the electric field, because electrons go opposite to the electric field. It's just a definition. So there's a drift component due to the electric field that causes a general movement of the electrons in the correct direction, even though that movement is much smaller than the actual physical movement of the electrons due to random thermal velocity. And so that's described by a relation like this that looks linear, where the current flux J is proportional to the elementary charge times the charge density N times the average velocity. And that is related, and this average velocity of the electrons is related to the electric field by the mobility, through a function mu of the electric field. So this mu of the electric field describes the effective velocity of the electrons as a function of the electric field. This is the so-called drift equation. And for small electric fields, by the way, I apologize for this vector. This is just a vector flux here. For small electric fields, then it's just proportional to the electric field times the mobility constant. So for electric fields that causes velocity much less than the thermal velocity, which is about 100 kilometers per second at room temperature, the relationship is linear. And this is measured a long, long time ago, like 50, 60, 70 years ago. And it's described in a beautiful plot, very famous plot. It appears in Andy Grove's book, the famous green book of semiconductor physics. By the way, you guys know who Andy Grove is. He's the guy who he's one of the Fairchild 8, and for a long time ran Intel and grew Intel to be the major semiconductor company in the world. So Andy Grove is a device physicist, very smart device physicist, Hungarian, came over the river with nothing on his back, except a suitcase, and made himself up. He really got the American dream. But anyway, in his beautiful green book, he has this plot of the velocity in centimeters per second, the drift velocity of electrons in silicon, versus the electric field in volts per centimeter. This is actually, I think, tens of thousands of volts per centimeter. And you can see here, it's a little bit different for electrons and holes, but for small electric fields, the electron mobility and the hole mobility are linearly related to the electric field. When the electric fields get really big, and it does get big in real transistors, then it's not linear anymore. It follows some more complex relationship. It finally saturates at the thermal velocity of the electrons. So somehow you can't make them go faster than their actual thermal velocity. And here you can also see the effect of this effective mass ratio between electrons and holes. Because the holes are more massive, they move less under the electric field, and so the slope for the holes is about 1/2 in bulk silicon compared to electrons. So that's how drift velocity is related to electric field. Now, what about diffusion? Diffusion, remember I showed you before the electrons going through the channel of the transistor? the diffusion is actually a function of the concentration ratio, as I'm going to show you now. A density gradient causes carriers to diffuse. So if there's lots of electrons here and few here, they're going to diffuse to try to equalize the density. And this diffusion current is described by a similar equation. The current flux caused by diffusion is equal to minus a diffusion constant times the charge of an electron times the spatial gradient of the charge density. So in this case, it's linear with the gradient of charge density. Very simple, right? It just says that they go minus in the direction of the gradient. So here, the gradient is increasing that way, right? There's more electrons over here. So that means they'll diffuse to the right, proportional to their gradient. Okay, now you might ask, are drift and diffusion somehow related to each other? They both describe movement of charges of a system that's somehow close to thermal equilibrium. And is there some relation? You know, one is the movement of charge by electric field, and the other one is simply the movement of charge because of diffusion. On the face of it, you know, it's not clear that there should be some relationship. And it was actually Albert Einstein who, considering Brownian motion, you know, thought really deeply about this stuff, and he realized there's a fundamental relationship between drift and diffusion, which is much later known as the Einstein relation. And it turns out that drift and diffusion are related by the Einstein relation. And if diffusion current is equal to what I just showed you, and the drift current is equal to mobility constant times the elementary charge times the charge density times the electric field, then it turns out that this diffusion constant here, which we don't have a number for, can be obtained from the mobility by multiplying it by this magic quantity, the thermal voltage. And I'm not going to try to derive this for you, but it turns out that this relationship is very deep and fundamental. So that means that the diffusion constant has the units of volts times whatever the units of mobility are. Mobility units, I believe, are centimeters squared per volt second. But anyway, this beautiful relationship. And so you can go read about that sometime if you want to see some beautiful fundamental physics. Okay. Does it matter for us now? Yes, because there's the thermal voltage here, and we need the diffusion constant because we want to compute the current through a transistor under this regime where charge is just diffusing through it, and all we know is the mobility, which we have the measurement of in this previous slide that I showed you the data of in Andy Crowe's book. Okay, so now let's talk about charges, fields, and potentials in a p-n junction. Okay, so first of all, let's imagine that we have a material which is n-doped. So we have lots of fixed ions. These are the ions of the donor atoms, and the mobile charge is represented by this minus, this red minus here. So these electrons are free here. Lots of free electrons, right? Very few holes. And then we also have on the other side, we have a p-type semiconductor, right? Where we've doped it with donors, acceptors, and we have lots of fixed acceptor ions with a negative vacancy, but they're fixed in the lattice, and mobile holes. What happens when you put those two things together? Then you get what's called a p-n junction. Of course, you actually have to grow them together so it's all a nice silicon lattice. You can't just like stick them together because all kinds of oxide junk on the surface. So when you grow this or diffuse this p-n junction, a very beautiful thing happens, which I'm going to show you now in the junction between n and p. So here you have this p-n junction. So remember, it's n-type over here, and it's p-type on the right. And now you have lots of mobile electrons here, lots of mobile holes here, both charge neutral, right? Because every time you have an electron, you also have the ion. So there's no net charge here, but there's more holes here and more electrons here and more holes here. So what happens? Diffusion comes into play, right? So there's an electron density gradient. Electrons diffuse to the right, right? Lots of electrons here, very few here. And there's also a hole density gradient. Lots of holes here and very few here, so the holes are going to diffuse to the left. And so the charge separation that builds up because of this diffusion builds up an electric field to pull the carriers back home. This is kind of very important, useful thing to remember. Whatever charge separation builds up because of this diffusion, it will end up pulling the carriers back home. It means it'll pull the electrons back to the N region, it'll pull the holes back to the P region. You don't have to work out anything. Just remember, carriers go home. That's a very useful idea, shortcut. So in a p-n junction with no applied voltage, drift and diffusion are balanced everywhere, all the time. Okay, so let's now look at the charges, fields, and potentials in a p-n junction. On the left, you have an n-type semiconductor with mobile electrons and fixed positive ions. On the right, you have a p-type semiconductor with mobile holes and fixed negative ions. And we can now look at the charge density as we cross the depletion region here, where the electrons have diffused over to the p-type side and the holes have diffused over to the n-type side, leaving this bare ions. This is a depletion region of fixed ions, positive on the left, negative on the right, and that creates a charge, a depletion region. I'll show you later what that means, that it's really depleted. That means, well, I'll just tell you right now, that depletion region means that the area is depleted below its majority carrier, in this case N or P density. But that results in a net charge density of positive charges here and negative charges here until it comes to equilibrium, where the diffusion current of electrons and holes equals the drift current of electrons and holes. So there's detailed balance of electrons and holes for drift and diffusion. And because you have this charge density positive here and negative here, you get an electric field. It's zero in the neutral regions, out here, and it goes up to a maximum here where you have the join between the positive net charge and the negative net charge. And the electric field is pointing to the right, because a positive test charge here will have all the positive charges pushing on it and all the negative charges pulling on it, so it'll be pulled to the right with maximum force. Now you can integrate this electric field to get the electrostatic potential. And if you do that, you start from, say, 0 here, and because the field is positive, pushing to the right, you have to do work. So the electric field will pull a positive test charge to the right? So you have to do work on this positive test charge to pull it to the left, and that's the electrostatic potential. It's the energy difference, the potential energy difference of a positive test charge between this side and this charge. This side, and this takes on a kind of a quadratic. It's quadratic here and it's quadratic here because you're integrating this linear function. In fact, if you go through the Fermi-Dirac equations and the density of acceptors and donors on each side, you can find that the value of this built-in electrostatic potential, the energy barrier, is exactly proportional to kT over Q. That's 25 millivolts times the log of the product of the concentrations over the intrinsic concentration. And so that turns out to be a voltage between 0.6 and 0.7 volts for typical junctions. So there's a built-in electrostatic potential. That's the built-in electric field or built-in potential barrier between N and P regions. And that's what you get in every NMOS transistor, between the N source drain and the P channel, or between the P source drain and the N channel, this electrostatic potential barrier. Yeah, so the typical built-in voltage is around 0.75 volts. Okay, you can't actually get energy from this barrier. It's kind of like just a built-in field or potential barrier, but you can't actually, it's a voltage, but you can't extract energy from this voltage. Okay, so that's the situation. You have this depletion region. So you have an electrostatic potential, which is the potential energy of the positive charge, which is positive on the N side and goes lower on the P side. And there's a built-in electric field pointing from plus to minus, pointing from N to P, that acts on a positive test charge to pull the hole back home and the electron back home to their respective majority regions. So the potential energy of the negative charged electron is just the opposite, right? Because you have to do work on the positive hole to put it on the left. In a similar way, you have to do work on the negative electron to put it on the right. So let's relate this to the band structure of a p-n junction. Remember, we have this electrostatic potential built in that in effect defines the Fermi level. So that's the edge of the conduction band. If the edge of the conduction band in the n-type region for electrons is here, because of the electrostatic potential, the edge of the conduction band in the p region is going to be up here, right? Because the edge of the conduction band is the energy of a zero moving electron. And so you do the same thing for the valence band, and then you get this so-called band bending between the bands of the n-type and p-type regions. And you have the intrinsic level is halfway between the conduction and valence bands, and the Fermi level is defined to be constant. By definition, if you don't apply an electrical field from outside, then the Fermi level is just constant throughout the region. And that is just the same way as defining in an indirect way that this is an n-type region because the Fermi level is close to the conduction band, and this is a p-type region, although less p-type doped because the Fermi level is close to the valence band. So that's another way of saying that this is n-type over here and p-type over here. Okay, this is all just to put you in the language of band diagrams so you'll be familiar with these things. Now, let's look at the carrier densities in a p-n junction. So this is really interesting, actually. So if you go through the Fermi-Dirac distribution and compute the exponentials of these electrostatic potentials, those are just exactly the Fermi levels, then you'll see that the concentration of electrons and holes on a log scale in the n-type region looks like this. N is here, and P is much lower than the intrinsic. On the p-type region, P is higher, it's more heavily doped, and so N is even lower. Remember this P-N balance? P times N is Ni squared, right? So the higher N is, the lower P is. But in the depletion region here, these concentrations connect together smoothly, but in a linear way. If you work it out from the exponentials, it's actually linear here. And the implication of that on the actual concentration is that on a linear scale, you see that the concentration of N goes to very low levels. If you go back to the previous picture, which I'm having difficulty doing here, I can't actually go backwards, but you'll see that the concentration of N and P is much below the intrinsic level throughout this so-called depletion region or space charge region. It's basically depleted of mobile carriers. The only charge that's around there are the fixed ionic charges. That's why it's called a depletion region or a space charge region. It's called space charge because there's spatially separated charge from these fixed ions. So now let's look at the IV characteristics of a p-n junction rectifier. The symbol for this rectifier is that the P is on the positive side of the arrow and the N is on the negative side, and you draw this arrow like this, and the diode is forward biased when the positive side is more positive than the negative side. So if you now plot the current through this diode, what you observe is that the current increases exponentially when you make the voltage positive, and it goes down, it's zero when the voltage is zero, right, when you have equilibrium. But when you make the voltage negative, then the current goes in the opposite direction. So the N is higher than the P. So the current should flow in the negative direction, but actually it increases for a little bit. This is in kT over Q units, and then it saturates, kind of becomes flat. So you get a constant reverse current. So the question is, what causes this reverse current? So let's look at this reverse bias p-n junction. Okay, now what you have to realize is that all the time this thing is under thermal equilibrium, and all the time there are new electrons and new holes being created on both sides of this junction. So let's imagine that you put +1 volts on the n-type region relative to the p-type region, which you tie to ground. So now you're reverse biasing the junction. You're trying to put positive charge from left to right. But remember, there is no mobile positive charge over here. There's only electrons. Mobile electrons. Here, there's only mobile holes. So there's really no current that can flow, right? There's no source of this mobile charge that can actually flow towards the right. So you take this original built-in electric field and you add an additional field to it. So you even makes the energy barrier higher. Okay, and what that does is it actually makes the depletion region stretch apart. But somehow, this voltage, which you've applied, this additional +1 volts, has to appear across this junction. How can it appear? Well, it has to expose more of the space charge to make that field appear. to take up that voltage, because there's no way you can create that voltage without having more charge separation. So what happens is that the depletion region gets wider. Nope, it's not like more charge builds up here, because these are just the density of the fixed ions. You get exposed more space charge. So that's the first thing that happens when you reverse bias a junction. The space charge region gets wider. The second thing that happens, you can observe by looking at the band diagram. Again, you have the N-type region here and the P-type region here, where the Fermi level is close to the conduction or valence bands. Now you put on the reverse bias. What happens is you increase the energy barrier by 1 volt. Remember, it started out at 0.75 volts. And now what you have is a quasi-Fermi level. It's not a thermal equilibrium anymore, but you can still say it's close to thermal equilibrium on each side. Now you define this quasi-Fermi level on each side with this applied voltage of 1 volt. So it turns out that the reverse current that you observe comes from generated electron-hole pairs in 3 different regions. The first region is in the N-type semiconductor, where now you can thermally generate an electron-hole pair, or in the P-type region you can generate an electron-hole pair, or in the depletion region, the space charge region, you can generate an electron-hole pair. In each case, something can happen. For the electron-hole pair that's generated in the depletion region, there's already a very strong electric field here, and so every time you generate an electron-hole pair here, it just instantly draws the extra hole to the right towards the P region. Remember, carriers go home, and it draws the electron to the left. Remember, the electric field points in this direction here, so it pulls on holes this way and it pulls on electrons this way. If the electron hole pair is created in the N or P region, there's no electric field out here, but still the created here is just part of this majority electron population, but the hole can diffuse around. If it diffuses around sufficiently to get to the edge of the space charge region, all of a sudden it starts feeling a very strong electric field, and so it just shoots the electron, the hole across. Same thing for the electron here. It might recombine with a hole, might just fall back onto an atom, or it might diffuse around at the thermal velocity, and if it gets to the edge of the depletion region, it can shoot across. And so there, you can define a diffusion region, a diffusion length. It's kind of an exponential length that defines the volume of space over which you effectively collect these electron hole pairs. And these 3 currents together define the reverse current behavior of a reverse bias junction. And this is the reverse bias junction leakage current that this creates. So now I have a question for you. If I take a junction, like I just showed you, and shine light on it and just measure the current, not applying any voltage at all, what happens when light shines on the junction, and which way does current flow? Here is the junction. I'm going to shine light on the junction. So what does that do? Well, when I shine light on it, as long as it's visible light, it makes electron hole pairs everywhere, but just like thermal generation does. And so that's going to end up creating a current which is flowing, a positive current, positive charges flowing into the P-type region. In other words, it will create a current that tries to forward bias the junction. It will create a current going in this direction across the junction. Right? So the current will flow from the N to the P across the junction. So the answer is that light tries to forward bias the junction, and you can measure that current, and that's basically the solar cell effect. That's the Einstein photoelectric effect in semiconductor. So now the last question I'm going to ask is, what's the capacitance of this reverse bias PN junction? And this is important because every transistor, CMOS transistor, is built out of these junctions, and every one of the source drain regions, and every time you build a photodiode, it has a capacitance. The capacitance is the capacitance of this separated charge here. So what's the capacitance of the reverse bias PN junction? So capacitance is defined by Q over distance, right? But now it's an interesting capacitance because the more voltage I put on it, the more the charge is separated. So the lower the incremental capacitance. Remember, the further apart the charge is separated, the lower the capacitance, because the electric field has more distance to work over. So capacitance is equal to Q over V, right? And it's also equal to the dielectric constant divided by the distance. So since the capacitance equals the permittivity divided by the separation of the charge, as V increases, L increases. So as V increases, the capacitance, the charge stored per unit voltage decreases. The bigger the voltage, the less charge you store per unit voltage. And so the effect is that if you plot the capacitance as a function of voltage, it goes down with voltage and the length goes up. And that's the difference between a normal capacitor, which has fixed plates at fixed distance, and a space charge capacitor. Okay, so we covered a lot of basic semiconductor material here: insulators, conductors, and semiconductors, the crystal structure of silicon, the band structure, the valence, conduction, and forbidden bands, holes and electrons, mechanisms of charge transport by diffusion and drift, doping with donors and acceptors, the Fermi-Dirac distribution, the law of mass action where NP is equal to Ni squared, a PN junction, and a reverse biased PN junction and its capacitance. And next week, what we'll cover is understanding how MOS transistors work in the subthreshold or weak inversion region where the current flows by diffusion from the source to the drain of these transistors. Hope you enjoyed this. If there's anything you don't understand, please ask questions or look at the slide again. Thank you. I included this extra slide, which is about properties of materials in silicon and silicon dioxide, and its important properties are germanium, silicon, gallium arsenide, and silicon dioxide at 27 at room temperature. In particular, it's a table that includes the number of atoms per cubic centimeter. You see it's 5 times 10 to the 22. It's a little bit different than what I showed before. The space constant in angstroms. An angstrom is 10 to the minus 10 meters, or 10th of a nanometer. The energy gap, that's the band gap, 1.1 eV. The effective density of states in the conduction band and valence band in number per cubic centimeter. You see it's around 10 to the 19. To compare that, it's about 10 to the 3 times less than the density of silicon. The intrinsic carrier concentration, 1.4 times 10 to the 10. And the lattice intrinsic mobility in centimeters squared per volt second for electrons and holes. It's about 1,000 or 500 centimeters squared per volt second in the bulk of the silicon. This doesn't apply along the surface of the silicon where stuff hits, the carriers hit the surface, but in bulk silicon, these are the mobilities. And the dielectric constant, right? The dielectric constant of silicon itself is about 12, but the dielectric constant relative to vacuum of oxide is about 4. And you can see the energy gap of silicon dioxide is about 8 compared with the energy gap of silicon, which is about 1.1. These numbers are really useful for doing hand calculations like you need to do for the lab exercises. So keep that in mind.
Okay, that's it. That's a lot. So now I've got a little quiz for you. Are you still there? Here's a puzzle for you.
Colby, I think there are some questions from the students. Maybe you can.
Let's see. Let's ask the question. So if we have questions when we rework the lecture, how can we reach you and whom? The specific lecturer. Yeah, you should ask the specific lecturer the questions about the exercise, about the lecture material. And ideally, you should ask those by OLAT on the forum so that everybody can share the answer. So if you have questions to the instructors, ask them ideally. I mean, we need to make sure this OLAT forum works, because then, we don't have to answer the same question over and over again. Does that answer the question? By the way, you guys are welcome to show yourselves and just ask a question. I mean, I'd love to see you guys, right? Otherwise, we're just talking to a bunch of blank squares with names on them. It's different than a real class.
There's another question. Maybe Daniel, do you want to answer yourself?
Where is that question? Does the Einstein relation hold for strong electric fields where drift current is not linear anymore? Good question. I don't know. I'm not sure about that. I'm not sure about that. You have to go and read about it more. I can't answer that right away. Okay. Okay. So here's a little, yeah.
And there's a quite early question from Nicholas Greensmith asking if there's a way to get neuroplasticity in silicon.
Where was it again?
The very beginning.
Oh, thanks. Sorry about not seeing that. Very beginning, so I'm going up to the very top. I do not see any slides. Do we get chapter? Is there a way to get neuroplasticity in silicon? Yeah, there's lots of ways to do non-volatile memory technology. They all have their big drawbacks or advantages. It's a big battle right now in the industry, whether what non-volatile, what technology, what device technology will enable non-volatile. It means when the power is turned off, kind of permanent storage of some new memory state. You know, there's MRAM, which is magnetoresistive RAM. There's phase change memory. There's all kinds of things that are battling it out right now. They all have their big disadvantages and some advantages. Right now, the dominant technology, right, to do non-volatile storage of stuff is basically hard disk or solid state storage on flash. That's really still dominant. And yeah, all the other technologies right now for non-volatile storage are just kind of fighting it out in the market. But they're not generally available to research groups, except under very special arrangements from the fabrication houses like Global Foundry or Taiwan Semiconductor Manufacturing Corporation. There's a few big founders that are bringing that stuff online, but they definitely don't like to share it with academic groups. They share it directly to their potential customers. Yeah.
And the question about the lecture, I don't really get chapter that we discuss in the lecture. What?
The chapter in the book that discusses this stuff? Yeah, it's the first chapter of our book. You don't really need to read a book chapter. I mean, it's good to read such chapter, right? If you can learn better that way by reading a discussion in a book, that's good. But you can also learn it just by understanding the material in the slides. That's the level at which you need to know this stuff for this course. This is really introductory background, tutorial or context background. Later, we'll get much more specific about the transistor devices themselves, the equations you need to use, your intuition about the equations, how they work in the circuits. Okay, so I hope that helps. Now, let me give you a little puzzle here. So let's try to compute this thermal velocity of electrons. How do we do that? Like if you wanted to compute how fast electrons are moving around, can you see the blackboard here now?
Yes.
Okay, cool. So let me try this cool little tablet I have. And we want to compute this thermal velocity, V, right, in meters per second of an electron. So you have an electron, it's whizzing around. How do you compute that thermal velocity? Okay, so it's pretty simple. I mean, you can treat it like a classical particle here. You can just say that its kinetic energy, mv squared over 2, is equal to the average thermal energy. And let's say that it's just an order of magnitude calculation, but we'll say that it's 3/2 of kT, right? There's 3 degrees of freedom, 3 directions of motion, 3/2 kT. And so from that, you can work out what velocity is. So shall we do that quantitatively? So we know the mass of an electron is what? It's about, if you're a physicist, you know that you get these numbers drilled into you. It's about E minus 30 kilograms, right? And KT, we already know that, right? We know what KT over Q is. That's easy to remember. It's 25 millivolts. So from that we can calculate all this stuff. So we say that V squared is equal to, we'll cancel the 2 here. It's equal to 3 KT over M. And we know what Q is, right? So we'll put Q in the bottom and then we'll put Q in the top just for shorthand, right? And then we have, then we can just put out the numbers. We'll forget about the 3, right? It doesn't matter for the purpose of this order of magnitude. So KT over Q, well, we'll put it in. It's 3 times, let's say it's 2.5 E minus 2 volts. So that's the KT over Q. Then the Q, we put in the top here again, is 1.6 E minus 19. And we'll do everything in meters, MKS units. That's the charge in coulombs. And then we divide it by E minus 30. And that's it, right? That's all the numbers. And so we can put this together, 3 times 2.5 times 1.6, that's about 10. Let's say that's about 10. So we have E minus 2. So let's just do it here. E plus 1, that's the 10 from these numbers, minus 2 minus 19 plus 30. We'll put the minus 30 on the top. So what does that add up to? So it's minus 1, minus 20, plus 30. So it's E20. So that means that that's the V squared. So V is can't be right. Yeah, so V is the square root of that. E10 meters per second.
Sorry, V squared is E10. V is
E squared is E10. Okay. Oh, I see. Okay, that's a mistake. Yeah, so it's E10 here, right? Thank you for that. I knew that was off by 5 orders of magnitude. Okay, so it's E5, 10 to the 5 meters per second, divide by 1,000 meters in a kilometer. That's 100 kilometers per second. Yeah, so those electrons are moving around really fast, right? Even at room temperature. That's what you have to realize. Now let's calculate how long it takes an electron to cross a channel of a transistor at thermal velocity. So let's take a transistor that's of a realistic length, like 0.1 meters, 0.1 microns. So 100 nanometer long channel, right? That's kind of an analog transistor channel. And calculate the time, right? So the time of passage at the thermal velocity is 0.1 micrometers. So that's E minus 7 meters divided by this number, which is E5 meters per second. So that's 10 to the minus 12 seconds, right? E minus 12 seconds, or 1 picosecond. That kind of sets the time scale of transistors, right? This 1 picosecond kind of sets the maximum frequency that you can operate digital circuits, because it takes at least that long for the electron to get across thermally. Picosecond, that's a terahertz, right? So that kind of sets the upper limit. A simple calculation. Okay, you want another little puzzle? It has to do with doping. Okay, so here's the puzzle. So I'm going to take silicon, and now I'm going to grow in the surface of the silicon some N-type doping. And I want to make a photodiode, right? So this is N-doped. Okay. And now what I'm going to do is shine light on this thing. That's light shining down there, and I want to collect the electrons in this N region that's built in a P-type subregion down here. Let's draw it in white here. This is P-type down here. Let's draw it in yellow. Actually, we'll use kind of yellow for the P-doped region. So this is an N-type surface region that's meant to be as a photodiode. It's supposed to collect electrons. It collects electrons because remember, when you make electrons down here, they're minority. If they get to the edge of this depletion region, they're going to go home to the N-type region. So how should I now dope this substrate here so that I encourage those electrons to be collected? In other words, how should I vary the concentration of that doping to push the electrons towards that N-type region? Anybody have an answer for that? Let's assume that I can shoot in from here. I can shoot in acceptor ions into the silicon and have them end up somewhere with different concentration at different depths. How should I now dope it? Well, what we want is to push the electrons towards the surface, right? And electrons get pushed away from stronger doped P regions. So what you want is a doping profile where the concentration of P doping that you implant gets bigger as you go deeper. So what you should do is dope it very lightly, P-type here, more heavily and more heavily as you go deeper. And if you do that, if you dope it heavier and heavier as you go deeper and do this so-called retrograde doping, well, retrograde because it gets lighter. The doping gets lighter as you go towards the surface. It's a retrograde. And that's possible because now you can implant ions instead of just diffusing them from the surface. If you do that, which direction will the electric field be in this region from here to here? Okay, remember the electric field always builds up to resist diffusion. So this is heavily implanted as p-type down here in this region. Right, so the holes that you put in here are going to diffuse away from this, and electric field is going to build up to pull them back. So within this whole region here, you're going to get an electric field, I'll make it in blue here, that always points up the gradient of P, right? So in this region, the electric field will point like this. In this region, it'll point the other direction, right? But the important thing is that the electric field points like this, and so the electrons will be pulled in the opposite direction of the electric field. They'll be pushed up towards the surface. And so by controlling the dope, and that's good because then they'll have more likelihood of being collected by this N region and turned into photocurrent. So by this doping profile engineering, you can move carriers around in the silicon and push them away from areas that you don't want them. Okay, was that clear? Any questions about that?
Toby, I think we have a question asking, would an electron in metallic bond behave like this?
In a metallic bond, yeah. So could you clarify? You can, in a metallic bond, behave like that? No, it wouldn't. It has to be one of these mobile electrons that's in the conduction band of the silicon. So remember, this material down here, in this part of the picture down here,
it was for the previous example, not this one.
Oh, you mean for the other example of the velocity?
Yeah.
Yeah, the thermal velocity. Yeah, it's the same electron mass and has the same average thermal energy. I mean, remember, that's just the average thermal energy. Some electrons are going to be moving much, much faster. But remember this Fermi Dirac distribution, you know, you're going to have very few electrons, exponentially fewer as you go away from the Fermi level, that are moving at extremely high velocities. But the average velocity will be determined by the thermal energy. But you'll have this distribution, which is basically a Boltzmann distribution of these energies. And that's why when I showed you that GIF of all those atoms, electrons whizzing around next to the channel, that's really the situation. You have a few high energy electrons that can get over this energy barrier and get into the channel and create current. Okay, good. So I guess that's enough for today. I'll share the whole recording of the lecture, which is basically the same as what I already recorded. And if you have any other questions, then please ask them on the forum of the OLED, which I'm going to now try to show you, just for the purpose that we actually look at it together and make sure that it's working. Let's look at that thing. So if you go to the course, this is the editing view, but if I go out to the course here, I think I'm like signed out now. Okay, start it. And there should be a forum. Let's see if that works. You should be open new topic. Okay, let's just try to see if this forum works, all right? I don't think we ever actually used it before. But if you do that forum, then everybody can see your question and the answer to it. And then we can build up a kind of a fact or a knowledge base. I'll give that a try. If that's not working, we'll figure out a better way to do it. But at the moment, that should be the forum. Okay, good. So now the doodle, right? Let's look at the results of that doodle together. Do you now see the people that registered or not? Or do I have to go to the edit link? Let's see, how do I have to refresh it here or something? Okay, so I see now, let's look at this, the results of that. So nobody likes Thursday morning. Probably there's some conflict in the class or something, or doesn't want to do the beta. The beta subject. And nobody wants this slide. You know, a few people want that. So what's the situation now? Yeah, and how many people in total are signed up? So 3, 5, let's see, 3, 5, 8, 12 plus 7 is 19 plus 8 27 out of 50 people. So only about half the people in this course actually signed up for exercise slot. Now, we need your feedback immediately, like right now. What is the situation with these exercise slots? Because I see there's now there's 30 people in the lecture right now. Actually, we've reached the end of the course. So you need to give feedback to Chen-Chi exactly about what's the problem with these exercise slots. Okay, does anybody have any feedback right now? You guys are a bit shy. The issue is trying to form groups. Yeah, I think you just have to sign up for a slot and then you'll form the groups on the fly. I'm not sure how to solve this problem. You know, this is the first time we've faced this situation ourselves. How is it working in other courses? Do you have any feedback in other courses for this? If you have suggestions on better ways to do it, please let us know, because we'd like to also improve matters.
I can also open a session so people can, maybe right after this class, so people who haven't found a group can discuss what they would like to do.
Yeah. Now, some of you guys know each other from particular departments. Others don't know each other. Others just got here as new master students and stuff. You know, you have to kind of take your random shot. Right now, you just have to get going at all, right? So just join up with anybody, ping somebody. Otherwise, Chen-Chi will just form the groups for you if you sign up for a slot. You know, when you guys meet in the Zoom, he'll just say, okay, you two pair up, you two pair up. You know, is that okay?
Oh, actually, they should pair up and meet in the. They should pair up physically and link to Zoom.
Yeah, so the best procedure that Chen-Chi recommends is you physically, two people actually sit nearby each other. One can then participate in the Zoom session, and the other one can actually run the notebook. If you're assuming that you just have a laptop with one screen. Of course, if you have a nice desktop, you know, like me with my four screens around me here, then it's easier, right, to look at multiple screens. But to actually get help from Chen-Chi and to see what he's doing on his screen and have it also running in a separate notebook on your screen, it's much better to have two people who can help each other. Does this make sense? Okay. Okay, so that's it. Sorry to go over time. So see you, I guess Chen-Chi will see you. I'd love to hear your feedback and, you know, ask your questions on the forum, and see you next week.
Just the last word. I will open a Zoom. Probably I will open a Zoom session for right now, so you can join.
Yeah, Chen-Chi will open the Zoom link. That is the link that's put in the first slide, which is a different one than this one. So go to that first slide in the slides that I shared, and you can get that Zoom link.
Yeah, so you can ask me questions about labs and stuff.
Right. And by the way, all those links for the lecture, the exercise, and the recordings are also in the schedule on the OLAT at the very top of the schedule, which I guess most of you have seen. Okay. Okay, bye-bye.